Our next speaker is Jacob Biamonte with his talk, Quantum Computing, from Science to Business.
This is just kind of a random assortment of slides, and I put a title on it that kind of seemed like it would fit this venue. So if you came here expecting anything past the title and a brilliant blue tie, you might be gravely disappointed. Nonetheless, we will continue. And so this is a graph that can facilitate your conceptual framework to understand at what rate quantum technology is being commercialized or attempted to be. And you can look at this is from Cypher. And so you can look at the technology trends as this stuff is starting to become patented and these sorts of things. And now remember, it's going probably faster than this. There's a lot of patents that don't show up on this, right? This stuff's about, if you know anything about patents, there's a year and a half sort of segue before a lot of this data will sort of go in. And what you're seeing is, things are really starting to take off. And what does that mean? Well, what that means is that there's not a technology company in the world that doesn't have a CEO or a CTO or an annoying vice president of who knows what, okay? It's always the vice presidents that are so annoying, right? Because they all want to be the vice presidents. Like, hey, I took the job as a vice president. I didn't realize there's 5 other vice presidents. They want to be the vice president. Sorry, dude. But that annoying vice president comes to the CEO and says, quantum, right? And the word sounds kind of cool. What does it even mean, right? And so something's happening. So the company says, should we do it? And the CEO says, what do you mean? Do what? And the vice president of whatever the heck says, buy something. So you can get a lot of different people to talk about a lot of different stuff. But if you're going to get me to talk about something, I want to talk about us. And so what makes us? What makes me? What makes our species? And there really is undeniably something about quantum technology that touches us at our core. And that's why it's interesting, not just from the technology, but there's something deep about it. It's like the species, us, going forward, we will master it, just like space. And so we start off by saying, what are we? In order to say what we are, we have to describe ourselves. And it's our ability to describe ourselves that might make us even unique in this universe. I hope not. But to describe ourselves, we use something called information. And so what is information? What is it? Now, it's been around since the beginning, but it's more profound than that. So perhaps if we polled the audience, which is growing slightly, you could say that it were a set of symbols, musical notes. But the important part, and the part that relates to today's talk, is that information must necessarily have a physical embodiment and is therefore governed by the laws of physics. That is profound, that is innocuous, but the intersection between philosophy and physics is to make that statement, then put a bunch of math to it, right? Philosophy lets you describe something that you do not yet have a theory for. Physics describes something by providing a predictable theory. Physics is all about predicting the future. And so, in the early days of information theory, the first connection between physics and information was something very, very fundamental. If you have information and you discard it, that dissipates heat. Okay, it increases entropy. It dissipates heat. So if I take information on my hard drive and I erase this, that dissipates heat. Maybe it sounds simple, maybe it even sounds boring. It's like, oh, I thought I was going to learn about quantum mechanics, man. And you will. You will. But what about computations that dissipate minimal heat? So one of the early types of computers that physicists predicted exist were reversible machines that dissipate essentially very, very low amounts of energy, or essentially no energy. They're called reversible computers. So they'll do a computation, you get a result, but if you erase that result, you'll dissipate heat. And so if you follow, and I'm sure that there's some people in here and you do your studies and then you realize, okay, I have to go work in industry, so I'm going to read popular science books. And you read about the second law of thermodynamics. And it's this endlessly complex discussion about that. And it's in all popular science books in some framework or another that are on physics, at least most of them, any of the good ones. And so what is the second law of thermodynamics? It's kind of, you can just simply think of it like this. If you leave your room alone in your house, or you leave your kitchen alone in your house, provided you live alone, it just sort of turns into a disaster, right? Until the maid comes or whatever, okay? Now, the entropy and the disorder of the universe is always increasing. And the energy in the universe available to do useful work is always decreasing. And so a low energy or an ordered state can create useful work. And I know everybody's like, this seems to be going very far from quantum mechanics, but we're going to pull it back together in a minute here. And so a long, long time ago, people tried to build perpetual motion machines, perpetua mobiles. And they look very good when you draw them. You can imagine this. You can think, what is that doing if it spins? Those balls, they drop, and it will go forever. But why will it not go forever? Because you have friction. So you have to drive it. You have to drive this machine. And there was an old game that people used to play. And this actually dates back to James Clerk Maxwell in the late 1800s. And he said, okay, look, I want to build a perfect perpetual motion machine. And it's called Maxwell's Demon. And here's how it works. And this is a thought experiment. So in conceptual physics, you have these thought experiments and you put mathematics to it or some other principle to explain it. And here's how it works. You have a box and you have a demon. That's the thing in green. And you put a gas inside the box, a gas like the air that we breathe, okay? It's called a gas. And what you do is, this demon, it measures the particles and it separates them. It puts the high energy ones this way and the low energy ones this way. So it orders the system to extract work. This was not solved. People didn't understand why this machine couldn't be built. But the problem is this. Ralph Lander in 1960, he said something very important. And this was the first connection, I would say, between information and physics. He said that the demon has two choices: to make that measurement of that particle and to discard the information, which dissipates heat, or to store that information into a memory, which eventually fills up and must be erased, dissipating heat. So that resolved the paradox of that perpetual motion machine. And the principle goes back to the exact same thing that we started with. But I'll tell you something that's even more strange. It's even stranger than this. So this just gives us a concept. It gives us something to understand that the laws of physics are connected to information. But the stranger thing is how information affects quantum systems. So what we've been describing up to this point, this is called statistical physics, stochastic mechanics. Okay? Statistical mechanics. Different names for the same thing. That's this regime where things are very, very small, and you look at the collective effect of something statistically. Okay? But when you zoom in a little bit closer, at the very small scale, you have quantum mechanics. And to harness those effects, that's what people are working on in the technology sector right now. And so at the quantum scale, all physics is reversible. And there's no way to create a copy machine which copies arbitrary quantum states. There is no way to create a machine which completely destroys information. So you cannot erase information at the quantum level. Okay, you could discard it at our level, but in a quantum system, if it's closed, the information's conserved. It's very different. And actually, it's the leak of information that makes the chip get hotter and it stops functioning. And there's all these different bizarre properties of the information at the quantum scale. And you would think, so what? But there's more to the story. Whenever I try to simulate a quantum mechanical system using a classical computer, that is difficult. That takes time, computational time, resources. Actually, it's quite impossible to answer many questions about quantum mechanical systems using today's computers. And so the simple idea that got this one started, the philosophical idea, was just if a quantum mechanical system is difficult to simulate computationally, then it must inherently have computational power. That is philosophy, that's not physics. But that gets us started. And so we think of computation in terms of different types of problems, different classes of problems. And so one of my favorites, just kind of give you an idea, is an old game, Kronensberg, and now in Russia, Kaliningrad. And so the idea is you walk across each bridge, never crossing the same bridge twice, and having a beer on every side, okay, ending where you start. And to solve that question, we invented something called graph theory. And by the way, for people that want a copy of these slides, they're actually on the internet. So I put all my stuff's open source. So, but don't discourage you from taking pictures. But if you do want it, you can have it. So now, Euler converted this to a graph. And he showed that there was no cycle in that graph. So it's impossible to do that. And the nature of the question is just to answer yes or no. But the point is, to solve that question, you have to imagine all possible paths. Okay, you have to show that no possible path exists. How do you show that no possible path exists? Well, I like this idea because it really shows that we have the intuition to think of things going in, let's say, all directions at one time. And quantum mechanics is notoriously famous for kind of saying that conceptually you have to think of something as being in two different places at once. And this is a computational problem. It's called a decision problem. And these types of problems, this class of problems, is the class of problems that quantum computers, which we have today, are quite going to be reasonable at solving. And so the first questions that people always ask is they ask, well, how fast can we solve a problem with a quantum computer? What resources does it require? And, et cetera, et cetera. And so quantum information and quantum information processing, it will utilize the quantum effects of a system and these strange quantum properties to be able to solve problems such as that traveling, this graph problem, this beer drinking problem. Okay, you want to go on some kind of bar tour. And I'm going to tell you the two main conceptual ways of thinking that quantum programmers use to kind of conceptualize and visualize what their quantum programs are doing. And the language to program a quantum computer is completely different than a classical computer. The classical computer will be programmed with Python to control the quantum system. The quantum system itself, it's more like an analog device. It's governed by physics. That's it. So the first one, the old saying is that the quantum lion cannot be caged, right? And so in the normal world that we live in, if I were to take a ball and I were to throw it, it would bounce off the wall. Okay, let's say it's a bouncing ball, right? Because the ball does not have enough energy to penetrate the wall, so it bounces back. In the quantum world, you have these things called resonances. And you can have a particle with less energy than the barrier that it hits into bounce back and go through the wall. Why is that useful? Because sometimes the computational problem that we're trying to solve is about finding the lowest point. And so if you can imagine a thermal machine, you would try to make jumps to go over these barriers. You can do that quantum mechanically. You can jump over, but you can also go through and then decay and try to find the minimum. This is a bizarre thing, but not quite as bizarre as the next one. And they're kind of related. And so quantum parallelism is the concept that you take a regular memory, okay, a normal computer memory, which can be in, let's say, some finite number of states. And this quantum register can be in multiple states at the same time. So in other words, the instruction point of your computer can actually be acting in parallel inherently. Okay, so it's very different than kind of a traditional computer. And all of these different computational paths will actually be assigned what's called a complex number, like an amplitude. Okay, so the whole thing is just kind of this big mess. What do we do with it? Well, we slowly work to sort of, you don't have to understand this stuff completely to be able to use it. So somebody, like Richard Feynman famously said, no one understands quantum mechanics. Okay, so people are alive today that understand it better than him, by the way, but there's still some open questions, many open questions, and there's this philosophical resistance. Human beings don't like the concept that the world is fundamentally probabilistic, that the future is inherently non-deterministic, that things can be in multiple places at the same time. And the reason we don't like that is it's so non-intuitive to kind of our experience that we have. And we don't understand this connection between the very small and the large, the macroscopic world that emerges. And no one actually cared about any of these things I was ever saying in any of this field. There was not very many of us until people suddenly started spitting these chips out, right? And so then they said, well, we have to find people that are going to program these things. Who are these people? And so they hired a bunch of people. I don't think they really know what they're doing. And now you have basically quantum in industry. And you have these beautiful, beautiful feats of engineering. And what these people did, it's really amazing. These experimental physicists who have basically destroyed theoretical physics, they went to the governments and they said, oh, all the applications are there. We just have to build it. It's far from the truth. And they said, oh, you build it, we're going to crack all the encryption. And then they built something and they said, oh, by the way, there's these new applications that actually work. We're not going to do what we actually originally promised. And so the new applications that everyone's excited about are here today now, and they're very new. We don't know their limitations. And so I'm in a research group. I lead a research group. And my research group, we try to break this stuff. We're not trying to show that it can do something. We're trying to show what it can't do. Okay, we're like the adversary. We're like the nemesis. Okay, because that's science, right? So these are beautiful. These are, this is all over the news. You guys can read all about that someplace. And the markets are expanding dramatically, right? And so we have this like special techniques from business analytics, and we're doing all these different tricks and blah, blah, blah. And most of it's not in these slides because it's just really boring stuff. You can basically take a bunch of data and look at different problems in your corporation and make some little, chart to sort of assess the risk and reward. Everybody knows how to do that, right? You can hire McKinsey to do that. But in reality, where is everything today? Today, things are moving very fast. Things are changing very rapidly. Most of the market today is, of course, educational, and there's a lot of side markets that have actually emerged that are very interesting, refrigeration being one of them. Making things cold is very, very interesting. And this is old. This is super old, and this is only 3 years old. This is so old that you shouldn't even be in my presentation. Okay? That's how little I care about this talk. Okay? This is nonsense. Okay, so if you want some real data, there was a new paper that just came out in Nature. They said that the startup funding per year is about 450 million. Okay? That does not include the government funding, which is billions. That does not include the major corporations that are funding their labs, which is billions. So there's really billions being invested into this, and we've never seen it before. 3 years ago, this didn't happen, okay? Right when this was happening, I started to write some papers that had the word machine learning and quantum in the title. Okay, other people did too, but they weren't as good at it as us. And so our stuff just exploded right as these companies started to build these things. And many of the stuff from quantum mechanics, you know, people that are experts at machine learning, they know that statistical physics influence machine learning tremendously. And quantum mechanics is quite close to some of these models, and you have some kind of interplay there. And the world is changing. This is so out of date. This will be the last time I ever show this. I say that every time. And so, where are the experts, right? They estimate now that there's 1,000 people that can program these chips. And the truth is that everybody, you know, what's happening is, and we're kind of in this very bizarre period right now because people think, oh, well, it's just like machine learning, we'll be okay. It's like, okay, guys, look, this requires real scientists. Okay, no offense to machine learning, okay, but like, you know, you take a guy out of a lab doing like quantum computer algorithms, and they'll learn machine learning in 3 weeks, and they'll start to kind of give feedback to the people, right? It's a different kind of scientist. So what the companies have done right now is they made it impossible for me to hire postdocs, okay? Because if you get a PhD in this stuff, even if you're not very good at it, they're offering these people a couple €100,000, and they're gone, and I just can't compete with this anymore, and it's just like driving me nuts, okay? So, you know, we're still doing okay. Our lab is still growing, but it's very difficult. And so industry is really drying up the academic research. And industry isn't trying to break things. They're just trying to show that it can do something. And so I think that this is, you know, if we learn something from the machine learning community, you know, machine learning researchers in industry are better than the ones in academics. This used to not be the case, okay? But quantum, maybe this will actually happen to us as well. It's starting to happen now. And so what do you do if you want to make a quantum startup? Right, so first of all, how many minutes do I have left? Because I'm going to offend everyone now. So I think startups are basically nonsense, okay? There's a bunch of whiny little kids that are going to fail, okay? Right? And it's just a bunch of nonsense. It's like, don't take VC money, just go do something. Just get a job and do it at nights and do it on the weekend and just do something real. You know, work with your brother, work with your family, just make something and just shut up. I don't care. No one's going to give you any money. They're going to watch you, and they're going to copy you if it works. So just face reality, guys. But if you're going to do it, and also what should be happening is screw the startups, because people at big companies, they know where things are going to move. So just do a little R&D leg over here. Here's the ingredients, kind of for any field, right? So this, it looks kind of silly, but this is actually very important. Quantum technology is not just the computation. It's using quantum mechanics to get data from the world, to get information from the world. Okay, it's like scaring me. It's like this is, you know, it's like the red in your face, like the whole thing. Yeah. So this is very, very important, this diagram. Why? Patent this stuff. patent things that look like this picture, and you can sue people later, I promise, okay? And so what are the industries in Poland that will be the early technology adapters? So what makes Poland unique? I know what makes Moscow unique. I know what makes certain towns in Italy unique. But what makes Poland unique? Where is Poland strong? I don't know the answer to that. If you know the answer to that, I would love to hear that. It's an important question because those unique features of Poland are going to dictate where your early adopters of this technology will be. And the two things that quantum is going to be good at first, now remember, depending on who you talk to, I look at these as horizontally across the board facilitators, and your vertical platforms are your different target domains. Some people say that backwards, but artificial intelligence is a horizontal enabling platform. You have to find those vertical pillars that are specific for your field, for your company, for where you fit in. And machine learning in general is too slow. Quantum mechanics will make it go faster. That's it. It does other things as well, and it can improve accuracy. That's just it. Quantum simulation of materials, beautiful stuff. Beautiful stuff. Quantum mechanics simulates itself very, very well, okay? That's the one thing that it does perfectly well. And this will transform this will create new industries because it'll give us ways to answer questions about materials that we just can't answer right now. We have to fabricate these. We have to synthesize. And these two things, the machine learning, the artificial intelligence, the simulation of materials, those are kind of the workhorses of this quantum tech. And that diagram I gave you is sort of how the thing sort of fits together. And the question is, where are the unique needs of Poland? Where are the unique needs of your company? And how can those two concepts with that diagram sort of be applied? So some companies say, oh, well, you know, I need better sensors actually, right? Other companies are more data-driven. Okay, so they don't care where the quantum sensors come in. They care about more, you know, the data processing side. And maybe, just maybe Warsaw, you know, definitely has a good mathematics, good physics, good science, good computational background. Maybe you'll see more quantum software startups here. But I don't want these to be traditional startups. Just find a friend and just go do it. Start talking after you have something, okay? You don't need anything else. You need something to work. You need it to actually demonstrate something. So maybe Warsaw can be very important for quantum software. I think it could be. I think it has kind of an ingredient. So I gave a talk yesterday actually at the Google campus for the Warsaw Quantum Computing Group. And those standing room only. There's all these young scientists. You know, it makes people excited. It goes back to the very beginning of the talk, and I'll end with that. There's something very humanistic about this topic. There's something that's kind of profound, like conquering space, conquering the very small. And yes, there's an economic benefit to all of this. But even without that, I still think it's somewhere that we as a species we have to go. So if you have any additional comments or questions or complaints, or if you want a copy of the slides, feel free to send me an email. And I think, is there a question and answer session now? Okay, do we have time for that?
I'm going to ask you.
Hi.
So you're based in Moscow?
Yeah,
You're
really.
actually based in Moscow?
I like it.
Do you hang out with Edward Snowden?
You know what? I thought about inviting him to give a talk.
Go on.
I haven't yet, though. Because well, here's the thing, okay? If I invite him, will he think it's like some kind of hoax? You know, like we're gonna take him out. You know. So how do we sort of like?
Isn't he in the airport? Didn't you pass him when you went through customs?
No, he's not in the airport anymore.
He's moved now, has he?
I think I deserve Edward as a friend, though. Edward, if you're listening, we could be friends. I'm a real guy. I'm not from the CIA.
Lovely. Well, thank you very much.